Alright, previously, in previous videos, we've been talking about limits as x approaches a of some function f of x. And we said that means as x is getting closer and closer to a, and maybe we have to worry about coming in from the right or coming in from the left, but as x is getting closer and closer to a, what's f of x getting closer and closer to, right? So as we approach a on the x-axis, what exactly are we approaching, the corresponding values approaching on the y-axis? And the picture I've drawn, it's continuous. So f of a would equal, it just ends up being equal to f of a. But now we're going to discuss something a little bit different. We're going to say, well, what happens as x goes to infinity or as x goes to negative infinity? And the definition works exactly the way you imagine it would. Instead of saying as x gets closer and closer to a, what we say is, as x gets bigger and bigger and bigger indiscriminately, is there any pattern in what the function is doing? You know, maybe it's going off to infinity. It's getting bigger and bigger. You know, maybe it's constant. It just stays constant forever. Maybe it goes down to negative infinity. Maybe it just oscillates, back and forth like the sine function or the cosine function, and it never settles in on anything. Or maybe it's not constant, but it eventually kind of just has a horizontal asymptote and it tends to some value as we go. So these are the kinds of behaviors. In that case, we would say, really what we're asking is, what's happening as x approaches infinity? We write it like this. The limit as x goes to infinity of our function, f of x. And similarly, instead of going far off to the right, you can go far off to the left. You can let x approach negative infinity. And we can worry about what's happening as x approaches negative infinity. And, the same kinds of pictures apply. So I think it's pretty straightforward. Let me just cover up some examples and go over a few tricks that that sometimes the professors like to include. All right, so first let's deal with some simple examples. Here's a function e to the x plus 4. And we can worry about, if that's our function f, what's happening as x runs to infinity, and what's happening as x runs to negative infinity. And let's think about how exactly we'd figure that out. So the limit as x goes to infinity of e to the x plus 4, well, you would say as x is getting bigger and bigger and bigger, what's happening to this term here, the e to the x term? Well, what does the graph of e to the x look like? Well, it looks kind of like that blue line over there. Alright, if I redraw it, it looks like this. So as x goes to infinity, as x gets bigger and bigger, e to the x also gets bigger and bigger and bigger. So this term that I've boxed is going off to infinity. And certainly, so infinity plus 4 is infinity, so you just plug it in. So again, you're allowed to just kind of plug in these values as long as you remember simple rules like 1 over infinity equals 0. But also remember that infinity divided by infinity and infinity minus infinity are what we call indeterminate forms. Right, so you have to do some kind of algebraic manipulation to figure those guys out. And otherwise, 1 over infinity is 0, infinity times infinity is infinity. Another indeterminate form to watch out for is 0 times infinity. That's also going to be an indeterminate form, and so on. So you just, you can plug in the infinity. You just have to remember that infinite arithmetic is a little bit weird. It doesn't satisfy all of the rules you would expect it to. And certain forms like this, and this in particular, they don't really make sense. And you can't tell what the limit's going to look like. So we'll see examples of that in this video. Alright, but that's not what we have here. If you plug in an infinity, you would want to say, oh, I get e to the infinity plus 4. I wouldn't write this on a midterm because it's not formally correct. There's no e to the infinity. Infinity isn't a number. But it kind of communicates exactly what we want it to communicate. E to the infinity just means what's e to the x doing as x goes off to infinity? Well, it's going off to infinity. It's like infinity plus 4, which is just infinity. Alright. So, and this blue line actually is the graph of that function, e to the x plus 4. So as we can see, as we go off to infinity, this blue graph is shooting up to positive infinity. Alright, what's happening as x approaches negative infinity of e to the x plus 4? Well, I had that little Must have erased it. Again, we have a sketch of e to the x, and it looks like this. It goes off to infinity and it has an asymptote to 0 as x runs to negative infinity, right? So as x runs to negative infinity, this box term is going to go off to 0, right? As x goes to negative infinity, e to the x goes to 0. So that would just be 0 plus 4. Now this is formally correct arithmetic at this point. 0 plus 4 actually is equal to 4. And so this green line is the line y equals 4. And as you can see, the blue curve approaches the green curve as an asymptote, and you can't tell the difference eventually. So the green one is the asymptote. And that's exactly what you would expect, right? This is the graph of e to the x. And what did we do? We added 4 on the outside, so you just shift the graph up by 4 units. And that's exactly what we have drawn here. Alright, so that's not a big deal. In this other example, we have something slightly different, e to the negative x plus 4. So e to the negative x, again, shifted up 4. And negating the x does what to the graph of e to the x? Well, since we negated it on the inside of the function, that means that we've flipped things around. We've kind of done a horizontal flip, which means we flipped around the y-axis. So that's exactly what this blue curve looks like. It looks like we've taken e to the x graph, except we've reflected it around a mirror in the y-axis, and of course we shifted it up by 4. So now the limit as x goes to infinity, e to the negative x plus 4 is equal to, well, now you plug in an infinity, you're going to get e to the, since it's a negative x up there, it's like e to the negative infinity plus 4. Again, maybe don't write this on a midterm, but it communicates the right thing. E to the negative infinity, what's e to the x doing as we go off to negative infinity? Well, it's going to 0, right? 0 plus 4, or just 4. And so you can tell this blue curve as we go off to infinity is approaching 4. And if we say, what's the limit as x goes to negative infinity of e to the negative x plus 4? Well, if you plug in a negative infinity, that's e to the negative infinity plus 4, which is just e to the infinity plus 4, which is just infinity plus 4, which is just infinity. Alright, so again, I can't stress this enough. Don't necessarily write this, but you can use this kind of reasoning to guide your answer. And it works exactly the way you would imagine it should. So here we have negative e to the x. This time we're multiplying by negative 1 on the outside first, which means first thing we do is we reflect about the x-axis instead of the y-axis. It's a vertical swap down. So it looks like this. And we still shift it up by 4. And so you can just immediately read it off. The limit as x approaches infinity of negative e to the x plus 4 is negative e to the infinity plus 4, which is like negative infinity, because e to the infinity is like infinity plus 4. And the negative infinity swallows the 4. So exactly what happens. I mean, as x runs off to infinity, this shoots down to negative infinity. So you just have to worry about the fact that, yes, e to the x is taking larger and larger values, but that minus sign means it's taking larger and larger values going further down the y-axis. And if you say, well, as x approaches negative infinity, negative e to the x plus 4, well, negative e to the negative infinity, e to the negative infinity is 0, so that's negative 0 plus 4, so there should be a plus there. Well, negative 0 is just 0, so that's just 4. So it works exactly the way you would expect. And just to cap things off, I mean, in all of these examples, it's going off to infinity in one direction and it's approaching the value 4 in another. I just chose the number 4 arbitrarily, of course, just showing you the kinds of behaviors that can occur. Finally, I leave this one to you. I don't have to go through this one, but negative e to the negative x plus 4. Let me show you some more interesting examples and tricks, though, for the kinds of weird problems that can arise. So let's consider this, and this is a big hint, so you guys should really pay attention to this part of the video. We have something like e to the 2x plus ex, I'll write it out here, e to the 2x plus e to the x plus 1, divided by 3e to the 2x plus e to the x plus 2. And you look at this, and what do you get? If you actually plug in, let's start with infinity. the limit as x goes to infinity, e to the 2x is going to shoot up to infinity, so is e to the x, so the numerator is going to swell to infinity. But so is the denominator. The denominator is also going to swell to infinity for similar reasons. So you're going to have an indeterminate form, infinity over infinity. So that's something we'll come to later on in just a second. But let's deal with an even easier problem for the moment. What's the limit as x approaches negative infinity of this monster, e to the 2x plus e to the x plus 1, e to the 2x plus e to the x plus 2. Well, now if we plug in negative infinity, e to the 2x is actually going to go down to 0. That would be e to the 2 times negative infinity, which is just e to the negative infinity, which is 0. And the same thing is going to happen to all of these e to the x type terms. They're all going to go to 0. So the only thing you're left with is the 1 here and the 2 on the bottom. 1/2. And indeed, you can kind of tell it has this horizontal asymptote at 1/2 as we go out to negative infinity. It also looks like it has an asymptote as we go out to positive infinity, but because that was an indeterminate form, we're going to have to do more work. So I'm going to take the time out and show you a very important trick, a trick that we're going to have to modify, so we're going to have to do a trick on a trick in order to handle this one. But first, let's learn the first trick. Very often, what you end up with is a quotient of two polynomials. Something like x cubed plus 2x plus 1 over, let's say, x cubed. Alright, maybe we have on the bottom something like x squared plus 2 or something like this. Or we can consider something like x squared plus 2. Let's flip it around. X cubed plus 2x plus 1. And then finally, how about something like 3x cubed plus 2x plus 1 over 7x cubed plus 4 or something like this. Alright, so let's analyze these guys right now, and we'll just take the limit as x runs to infinity, but it actually doesn't matter, as you'll see. Even if we let it run to negative infinity, we'd get the same answer, because there's going to be a little trick. We'll even let it go to negative infinity on this one. There's going to be a little trick. It works either way. Alright, so the trick is, and this is a trick worth remembering, if you're asked for the limit of a quotient of two, quotients of polynomials like this, a rational function like this, as x goes to infinity. So this is a trick you really only want to pull out of your belt when you're doing a limit as x goes to infinity. You don't really want to pull this off if you're doing just a finite value, like it's approaching 0, or it's approaching some of the zeros of the polynomials or something like that. In that case, factor. But in this case, you can do the following trick. You multiply both the top and the bottom by 1 over the highest power of x that you see in the entire expression. Numerator or denominator doesn't matter. The highest thing I see is x cubed, so I'm going to divide both the top and bottom by 1 over x cubed. Since I'm doing it to both, it doesn't change the actual value. So when you do that, what are you going to get? You're going to get an x cubed divided by x cubed is just 1. 2x divided by x cubed is going to be 2 over x squared, right? The x up top is going to cancel with one of the x's down here. You're going to be left with x squared on the bottom, plus 1 over x cubed. On the bottom, x squared is going to cancel two of these guys. It's going to be a 1 over x plus 2 over x cubed. Now let's take the limit as x goes to infinity of that expression. Okay, well, if you actually just plug in the infinity in the way we've been doing it, 1 plus, well, 2 over infinity, I mean, as x runs off to infinity, what's 2 over x squared going to go off to? It's going to go off to 0, right? As the denominator gets really big, the overall fraction is getting smaller, so that's going to go to 0. And in fact, so same thing is going to happen here, right? So all of those terms on top, aside from the 1, are just going to go to 0. So I'm not even going to write them. On the bottom, these two terms also, as x goes to infinity, they also go to 0. So we have a 1 divided by 0. So that's either going to be, remember, whenever you're dividing by 0, it's either plus infinity or minus infinity, depending on whether, and you have to actually plug in values to check what's happening. Now, for x running off to infinity, x is a positive value, so everything in this entire expression is certainly going to be positive. So if it's going to run off to any infinity, it's going to run off to positive infinity. Okay, so that handles that. But, okay, so yeah, so that takes care of that. So now let's move on to another one. The limit as x goes to infinity of x squared plus 2. And again, the highest order term I see here is an x cubed. So I'm going to multiply both top and bottom by 1 over x cubed. That's the trick. And you're going to end up with, I think, 1 over x, 2 of them cancel, plus 2 over x cubed over, and on the bottom it looks like we have a 1 plus 2 over x squared, right? We only canceled one of them. Plus 1 over x cubed, and I'll just do this real quick. This is going to go to 0, this is going to go to 0, 0, 0. This one's real easy, so this is going to go to 0 on top, 1 plus a bunch of zeros on the bottom. 0 over 1 is just 0, so it goes to 0. So that's interesting. So we have one of them going off to infinity, another one of them going off to 0, and just finally we have limit as x goes to negative infinity. Again, like I said, doesn't really matter because, you know, the real trick we're using here is when we divide by the highest power, you're always going to end up with x's on the bottom. And it doesn't matter if you let x go to infinity or negative infinity. If it's on the bottom, then it's going to go to 0. Right? So it really doesn't matter. So it usually doesn't matter whether the limit as x goes to negative infinity. But I'll say something more about that in a moment. But in this case, we're going to play the same exact game we've been playing. 1 over x cubed, 1 over x cubed. And what does that turn out? Well, that's 3 cancels the x cubed plus 2 over x squared. I'm doing this all quick mentally. Plus 1 over x cubed on top. What do we get on the bottom? Well, it cancels that out. We just have a 7 plus 4 over x cubed. Now we let x run off to negative infinity or infinity, doesn't matter. As the denominator gets bigger, bigger, and bigger, these are all going to go to 0. Right? I mean, I'm just using the fact that if you look at the graph of something like 1 over x, it has a horizontal asymptote. It approaches 0 as you go out to infinity. But you know what? It also approaches 0 as you go out to negative infinity. And the same thing is true for, 1 over x squared, except this branch would be, for 1 over x squared, it would be above here. But it doesn't matter. Either way, it's always going off to 0 as you approach infinity or negative infinity. Alright, so that's 3 plus 0 over 7 plus 0. That's just 3 sevenths. Alright, so before I address this, let me just point out a very important pattern that's always going to happen here. When you have the quotient of two polynomials, and you're taking the limit as x goes to infinity, if the degree of the degree being the highest order term, if the degree of the numerator is bigger than the degree of the denominator, which is what we had in this first example, then you're always going to go to either infinity or negative infinity. So the moral of the story is, I guess, is that the numerator grows faster than the denominator, so it wins out. If, however, the degree of the numerator is less than that of the denominator, which is what we had in the second example, again, the bottom term is going to win out. But now, if the bottom term is growing faster, the denominator is growing even faster than the numerator, it's always going to end up being 0. So that's the intuition behind this little trick that we've been doing. And then finally, something real interesting happens. If they have exactly the same degree, here they both have degree 3, then you can ignore all the lower order terms, anything other than that top degree, and you just look at the coefficients of those top degree terms, and that quotient is going to equal your limit as x approaches infinity or negative infinity. So that's a nice, pretty pattern that you can just immediately kind of memorize right away without having to go through all of this. Although, just in case you have to show work, it is important to remember that this is the trick. This is what you're doing. Now, I said something a little vague about, well, this might be plus or minus infinity. We figured out the limit as x goes to infinity of this guy, but we didn't really figure out the limit as x goes to negative infinity. If we take the limit as x goes to negative infinity, and by the way, This case, the case where the degree of the top is bigger than the degree of the bottom, is the only time where you'd have to worry about a difference between an infinite and a negative infinite limit. If we're talking about rational functions, quotients of polynomials, and they have the same degree, it's always going to turn out, whether this be the limit as we go to positive or negative infinity, it's always, you can just jump right to the end, you know it's going to be the quotient of those coefficients, of the top order terms. Ignore the lower order terms. And if you're dealing with something where the numerator has lower degree than the denominator, I don't care if you're going to positive or negative infinity, it's always going to end up being 0. But if you have a situation where the top order, the numerator has higher order than the denominator, then it could go either way. So for example, if we take limit as x goes to negative infinity, and we'll just use the same simplified algebraic version of it, 2 over x squared plus 1 over x cubed. Remember, that was just an algebraic rewriting of the original problem, 2 over x cubed. Alright, this is obviously, you plug in negative infinity again, it's going to be 1 divided by 0, but that could either be positive or negative infinity. So let's think about whether this is going to take on positive or negative values. Alright, so as x runs off to negative infinity, this is actually going to take on negative values, and this is going to take on negative values. So they're going to get closer and closer to 0, but it is negative on the bottom. So we're going to have a negative in our denominator. And are we going to have a positive or a negative on top? Well, remember, as x goes off to negative infinity, these terms are all approaching 0. So for very, very large negative values of x, this is going to be really small. It's actually going to be really small but negative. This is going to be really small but positive, because it's an x squared, not an x cubed on the bottom. Right? But it doesn't matter. As if x is really big in the direction of negative infinity, if it's a really large negative number, these guys, positive, negative, whatever, they're going to be tiny. They're going to be little guys, right? So it's going to be some small addition to the number 1, and the number 1 is going to basically take the lion's share of what's going on up here in the numerator. So this is going to be 1 plus or minus a little bit of an error term. Alright, but in particular, adding or subtracting a tiny thing isn't going to make this any less positive. So for very large values of x, the top is going to be positive because it's going to be close to 1. And the bottom is going to be negative. So positive divided by negative is negative. So this is taking negative values as x runs to negative infinity. And because you're dividing by 0, it's still 1 over 0. It's either positive or negative infinity. If it's taking on negative values, it must be negative infinity. So you do have to worry in this one case. So there are 3 cases here to keep in mind. What has the higher degree? The numerator, the denominator, or they have the same. Only in the case of the numerator having a higher degree, it's either going to be positive or negative infinity, and you should check. It depends on which limit you're taking. The limit as x goes to positive or negative infinity, and you need to think carefully about whether it's positive infinity or negative infinity. This one, the denominator has a bigger degree, it's always 0, period. Positive infinity, negative, I don't care, it's always 0. And same, it's always the coefficients, the ratio of the coefficients like we had here. Positive infinity, negative infinity, or anything. So this was a worthy digression. This is important to keep in mind and to kind of master everything we said with these ratios of polynomials. Okay, now that's not exactly what we have here. We don't have polynomials here. So remember back here, just as a quick review, we had this weird expression where you have e to the x terms. And we said as x goes to negative infinity, we just plugged in a negative infinity, and we saw that it ended up being 1/2, which was interesting. But what's happening as x goes to positive infinity? Well, infinity over infinity is an indeterminate form, and we'd like to apply a similar technique to what we had down here. So here's what we can do. The trick here was to divide by kind of the highest power of x that we saw. And we're going to do the same exact thing here. We're going to divide both the top and the bottom by 1 over e to the 2x. 1 over e to the 2x. What's this going to equal? E to the 2x over e to the 2x is going to be 1. E to the x over e to the 2, what is that? E to the x over e to the 2x is going to equal, well, you're taking a quotient in this way, you just subtract the powers, x minus 2x. Alright, but x minus 2 of itself, we're left with negative x. So that's plus e to the negative x plus, well, that's just 1 over e to the 2x. Alright, so on the bottom, let's see what's happening here. 3e to the 2x divided by e to the 2x, that's just going to leave us with 3 plus, again, e to the negative x plus 2 over e to the 2x. I could have written that as e to the negative 2x if I wanted to. It's the same thing, right? Now if we let x run off to infinity, this term is going to go to 0, right? Like we said before, up earlier on in the video, e to the negative x as we go to infinity is going to tend off to 0. Same thing is going to happen with these two terms. They're going to go to 0, and you're going to be left with 1/3. Right? So we did something similar to what we did here with the polynomials, or we could actually turn it into a problem of polynomials if we approach things in a different way. We could have said, you know, do you notice that e to the 2x is the same as e to the x squared, right? Because power of a power powers multiply. So if we called u e to the x, we made a little substitution. U is called, we called e to the x u, then e to the 2x is just u squared. And if we're asking, well, what happens as x goes to infinity? Well, if x goes to infinity, e to the x goes to infinity, so that's really asking, well, what happens as u goes to infinity? And if we write our expression here in terms of u, our expression is e to the 2x, which we agreed was u squared, right? U squared plus u plus 1, e to the x is u, over 3u squared plus u plus 2. And we'd be interested, as x goes to infinity, u, which is just e to the x, also goes to infinity, so we're really asking the limit as u goes to infinity. And so now we've actually, by doing this little substitution here, by giving e to the x a different name, we've actually turned it into a polynomial problem like we were talking about earlier. You would notice they had the same power, and you would have said, the coefficients are, there's implicitly a 1 in front of that one. It's just 1 over 3, and that's exactly why we got 1/3. So you can do it however you like. You can either just know to divide by 1 over e to the 2x, or personally, I like to think of it in terms of substitutions. Call e to the x u and then move forward. But this is a trick which shows that you can use this very well understood case of the ratio of two polynomials to also handle certain other cases here. It didn't look like polynomials at first, but a simple substitution showed that it actually did turn out to be polynomials. So now let's see one more trick, and we'll just do a substitution this time. How are we going to handle this guy? So I want to know, well, what's happening as x approaches infinity of 2 ln of x plus ln of x plus 3 on top, and on the bottom 4 ln of x plus minus ln of x plus 1. Okay. And so what we would do here, this is actually a poor example. I mean, obviously what you would do here is you would just say, well, 2 ln of x plus ln of x, that's just 3 ln of x on top, plus 3. 4 minus ln of x is 3 ln of x plus 1. As x goes to infinity, it's going to go to infinity over infinity. But what you could do here is say, well, if we call u ln of x, then x going to infinity means that the ln of x would also go to infinity, so u would go to infinity. So really what we're asking is, what's the limit as u goes to infinity of, well, now this is just u. So that's 3u plus 3 on top over 3u plus 1 on the bottom. This has degree 1, right? This is implicitly a degree 1 polynomial. This is a degree 1 polynomial. Alright, so it's just the coefficients of these guys. It's just 3 over 3, which is equal to 1. So this is another case where, I mean, and this is highly zoomed out version of it, but you can tell that it kind of goes to 1. It doesn't quite approach 0, it actually approaches 1 there instead. This is the graph. And you'll notice it doesn't make sense to ask, well, what happens as x approaches negative infinity? Because, well, for negative values of x, ln of x isn't even defined. So as you can see, there is no graph over here. It's not even defined over there for values x equals 0 or less. Alright, I thought this was going to be a more interesting example because I thought we would be able to bring these things up as a power, and you would have had an ln and so on. But you would have had ln of x squared. The square would have been on the inside. It just occurred to me that that's the case. So it was an example, but it was a less interesting example than I hoped it would be. But this is definitely an interesting example that shows you how you can do a simple substitution to take advantage of what we know about rational functions. So I think this video has gone on long enough.